All right, part two. Here's the lesson. I was kind of tempted to just give this to you and see what you remembered from functions and how you could apply that, the stuff that you've learned in calculus so far to help you with your sketches of rational functions. But here I am teaching my face off. Uh, for good or for bad for you, I'll let you decide at the end. Um, this is function stuff. So this is the notes about asymptotes and limits involving infinity, and we talked about this stuff during the warm up. And the second point was this idea of the degree determined where the horizontal asymptote is, um, and there's a reminder there. There's uh, a special reminder that if the top is bigger than the bottom, we know that there's no horizontal asymptote. But if it's the degree is higher by one, then there's an oblique asymptote, and we can get the equation of the oblique asymptote by using long division. And I think we saw an example of that just recently when we were coming up with a quick sketch. We investigate the end behaviors discussed in point two, the end behaviors by evaluating those limits as x goes to infinity or negative infinity, as we did in the warm up. All right. Skills involved in evaluating limits at infinity are reviewed in those examples, so don't be afraid to read that. We did it in chapter one, but you can get the textbook's uh, very thorough version of these examples on pages 185 to 189. So let's get to an example. So we can continue developing our curve sketching algorithm. Now, this is curve sketching from MCV4U, but also from MCV4U. It's kind of like what we've been doing this chapter, talking about increasing functions and critical points and domain restrictions and all those things. Are We're developing this idea of a recipe for curve sketching, and for rational functions, this will feel familiar uh, to what we learned in functions. So asymptotes, we check for domain restrictions, discontinuities, vertical asymptotes, holes. Yeah, in case we have a hole, whatever that is, we'll hopefully remember that if we see it. Evaluate behavior near the vertical asymptotes. That's that limit as x gets close to a vertical asymptote, and then find the horizontal or oblique asymptotes, all function stuff. Maybe with calculus notation dropped in there. Intercepts, x and y intercepts, and look for any other nice points. This is all function stuff, MCV4U. This is where we get into calculus. So the maximum and minimums and the intervals of increase and decrease, we use the first derivative test, right? So the idea where f prime at x equals 0, we investigate those critical points, and where it changes sign, we'll have a local extremum, uh, either a max or a min. And remember, increases where the first derivative is positive, decreases where the first derivative is negative. Notes about the sketching algorithm. So we got four things so far in our sketching algorithm. We don't have to complete the steps in order, and you may not need to complete all the steps for all questions. We might not need all this stuff. We don't have to necessarily go through all these steps, but we certainly want to paint a complete picture, and that's the journey that we've been on this chapter. All right, so let's get at some examples. There's four examples. I'm going to do this one and this one with you, and those two are I've attached the answers. Where are they? There's my answers, and I'll just let you add those to your notes. Okay, I don't think anything weird necessarily happens. I'll go through them quickly with you, but I'm going to do A and C. We'll do those together. So first of all, let's talk about the asymptotes. Right, that was the first thing in our sketching algorithm. Let's talk about the asymptote. So here's A for asymptotes. We've got a vertical asymptote at x equals -5. And what I like doing, by the way, this is my favorite way to do these, is here's my puzzle. Right now it's a blank slate, and then I start adding my evidence to it. So a vertical asymptote at x equals minus 5. And I might have to adjust this later, but this is kind of how I'm starting. I'm building my puzzle. So far, this is what I've got. What's next? Well, I'm going to have a horizontal asymptote, right? Horizontal asymptote at y equals 3. We knew that from functions because the top and bottom have the same degree, so we divide the leading coefficients. Perhaps we should show a little calculus work here. The limit as x tends to infinity of 3x minus 1 over x plus 5. This is the sort of thing we just went through. I factor out an x, so I get that idea of the zeros, right? When x becomes really, really big, this becomes 0. I take an x out of there, and I got 1 plus 5 over x. And so that's equal to, bing, bing, those cancel out. That's equal to 3. But if I'm clever here, I can think of this is a little bit less than 3. This is a little bit more than 1. So what this is going to do, this is going to approach the horizontal asymptote of x equals 3 from below, right? A little bit below 3 divided by a number that's a little bit more than 1 is going to be a little bit less than 3. And I'm just penciling this in here right now just because I'm not going to, it might not go nicely with my other evidence. What else might we want to do? Well, we might want to grab, I'm going to grab this if I can. Yeah, well, hang on. I'll call that A there. This is horizontal asymptote. And then I'm going to grab this, bring it down here so I can talk about, I want to talk about the behavior close to the vertical asymptote, right? So if we had, again, the limit as x approaches negative 5 from the left of f at x, what do we have? It's going to be negative infinity or positive infinity, isn't it? Now, we sort of do this rough work in our head. There's our function. When x is close to minus 5, this is close to minus 15, it's a minus. And then on the bottom, when it's close to negative 5, but from the left, that means a little bit to the left of negative 5, negative 5.01 and so on, this is going to be a teeny negative, right? So I got a negative divided by a teeny negative is a huge positive. So therefore, this limit is positive infinity. That means on the left side, it's going to go up like this. And convince yourself that similar calculation is going to get the behavior on the right of the vertical asymptote to go low like that. Okay, what else? Well, what do we have in our algorithm? Check for domain restrictions, discontinuities, check, all that stuff. X and Y intercepts, dandy. Let's do that. Change of color, change of step, intercepts. X intercept is when y equals 0. So I put in, where's my function? It's 3x minus 1, x plus 5, 0 equals. Right? As long as x can't be minus 5, I'll multiply by that there, and I get 0 equals 3x minus 1. X equals a third is the x-intercept. Right about there. 1/3. Not exactly to scale, but we get the idea. The y-intercept is when x equals 0. Put that in straight off. F at 0 is negative 1/5, right? 0, negative 1/5. Right about there. I think I can kind of see what's going to happen here. I never evaluated the behavior of this function when x went to negative infinity, but I have a feeling it's going to do this. And that is my first guess. I'm going to still work on this and add to it and reassure myself that this is exactly what's going on. But I'm pretty sure that, I'm pretty clear picture. But let's keep going. We had look for any other nice points. Well, do we need any more nice points? Maybe, maybe not. I'm pretty sure that I know what's going on. I'm still going to have to, it's calculus class. I'm still going to have to do the derivative and try and find maximums and minimums. So max and mins. Go down here in a different color. Max and mins in a different color. There's the function. I'm going to take the derivative using the quotient rule. Derivative of the first thing, write down the bottom, subtract, write down the top, derivative of the bottom, all over the bottom squared, x plus 5 all squared. Tidy up, collect up like terms. I have 3x plus 15 minus 3x plus 1 all over x plus 5 all squared. 3x's cancel out, and I'm left with 16 over x plus 5 squared. So note, f prime dne at x equals minus 5. Not a critical point though, right? Because the original function wasn't defined there. So that means x equals minus 5 is not a critical point. But where is f prime at x equal to 0? Well, notice if we solve this equation, as long as x is not equal to minus 5, cross multiply, I get no solutions. No solutions. So I think of the number line for f prime at x, number line. We knew it was undefined at minus 5. But on the left of minus 5, this expression, well, it's always positive. And on the right, it's always positive. Always positive. So that means our function is always, it's always increasing. So it's increasing as long as it's defined. Never decreasing. And notice, that's what our function, that's what our original graph showed. We have just proven that this function doesn't do any of these crazy stuff that we were worried about in advanced functions class. Doesn't come up and do that because it never decreases. It never decreases. This never has a maximum, local maximum or minimum, and we've just proven it. All right, dandy. Remember, I'm skipping B, and I'll do C with you in part 3 and quickly go through the other two that I am skipping.